Welcome again to my lecture on mass and heat transport. I'm going to continue this lecture. First, I'm going to review quickly the preliminary ideas that we laid down and introduce one more. And then the rest of this small lecture is going to be on the mass conservation and the species conservation equations. So let's first review the things that we've learned so far. So we have learned here that the Gauss's theorem tells us that the volume integral of a vector is equivalent to the dot product of the vector and an integration over the surface. So the volume integral of the divergence of this vector, so this is the divergence d omega over the entire volume omega, is equal to the integral of the vector over the surface. So let me take an example that we will use in a minute. Suppose that I have a position vector r, and I want to apply Gauss's theorem. So if I apply Gauss's theorem, then the integral over the surface of r dot n ds should also be equal to the volume integral of the divergence of this position vector r over the volume d omega. Notice that the divergence of a vector is just the sum of is a scalar quantity, so this is scalar, and it is the sum of d by dx plus d by dy plus d by dz of the three components. So the three components of r are basically x and y and z. So when you do this sum, you get a factor of 3, which means that if you look at this equation here, and then you can say that the integral of r dot n ds over the surface is equal to 3 integral over the volume of d omega. Omega is the element of volume, and this is equal to 3 times omega. So this is the total volume. And this is really a nice result because we can use it in many different ways. Next, we reviewed the fact that we have definitions, and we defined the mass flux, and the mass flux is J sub m mass equals to rho times the vector velocity v, and we defined the diffusion flux, and the diffusion flux is J diffusion is fixed application of Fick's law gives us the minus diffusion coefficient times the gradient of the concentration. Also, or the concentration sometimes for a species that has density per unit volume rho sub I, this will be essentially the concentration. So the diffusion flux of the species will be equal to minus d for species I, the gradient of, I'm going to put a vector here on top of the symbol of nabla to indicate that it is a vector, and this is rho sub I. And moreover, if we are now to write rho sub I as equal to the mass fraction m sub I times the total density, so this is total density, and this is mass fraction. Then the diffusion flux of species I is minus d sub I times the gradient of rho times m sub I. We will utilize that in a little bit. Then next we also defined the species flux, number 3, species flux. And the species flux is J sub I, and this is a drift flux. Drift is different from diffusion. So you can transport matter by drift or by diffusion. Drift, it means that you have the density of species I times the relative velocity of species I. And the relative velocity of species I is the difference between the actual velocity of species I and the average velocity of the mix. And therefore, if we define the average velocity of the mix as the weighted sum of the velocities of rho sub I, v sub I bar divided by the sum of rho sub I, then we can actually write it as the sum of rho sub I is equal to rho, then and rho sub I over rho is m, so it would be basically the sum of m sub I vi sub I bar, and that is an expression for the average velocity. So if we now to plug in this back in here, then we can see that the average velocity here is introduced, and the species flux J sub I is equal to now rho sub I v relative I, which is equal to rho sub I times v sub I bar minus the average velocity, and put the bar here on top to indicate that it is a vector. So the last definition in the preliminaries here is about chemical reactions. So in chemical reactions, I'm going to consider a chemical reaction of this form. I have A plus constant alpha times another species x sub I. These are A and X are symbols, chemical symbols for the different species, and we're focusing on species I reacting with another element A with a reaction rate constant K, and that produces two different elements. So the reaction rate is, we're going to call it omega, and omega, this is a chemical reaction number J. So this is a J reaction. In other words, species I can participate in many of these chemical reactions, as many J equals 1 up to n. So the reaction rate for this for this reaction J, or for this chemical formula J, is we're going to call it omega sub J, and it's equal to the reaction rate constant times the product of the concentrations of the reactants. So the reactants, the concentrations, we're going to put them in square brackets. However, since we have a stoichiometric coefficient here alpha, then the products are raised to the coefficient. So we're going to just raise this to power alpha, and each one of these is a concentration. So that's kind of omega J. So now if we have the species I is introduced in different reactions, we would have to collect or add up all of the contributions in what we call the reaction rate per unit volume of species I. Per unit volume for I. And this reaction rate, we're going to write it as R sub I dot means d by dt, triple prime means per unit volume, is equal to the sum over all of the reactions. So the reactions would be from j equals 1 to n of omega j times nu ij, and nu ij is the stoichiometric coefficient in each reaction. Like how many of the molecules are involved in each reaction, as we will study later in the CVD area. So that gives us kind of a preliminary idea about the different terms that we use. So if we look at it now, we will see that we have identified or defined fluxes, and the flux is either drift flux or diffusion flux. Diffusion is proportional to the gradient of the concentration. Drift is the product of the mass times the velocity, and we have to pay attention to the relative velocity if we have a mix. And we also introduce the concept of Gauss's theorem that converts from a surface integral to a volume integral, and that will be useful when we start looking at conservation equations. So I'm going to now work on conservation of mass, and so let me just kind of have a little bit of space here to start working on the conservation of mass with you on the side. So if we look at mass conservation, what I'm going to do right now is I'm going to write the equations for mass conservation for the total mass. So let's assume that I have a total mass and I'm going to conserve it. And in this case, I'm going to make a volume. So symbolically, I'm going to have a volume here. And this volume will have a flux that if it goes in, then it's positive. So J, a mass flux that goes in, that's positive. If it goes out, it will be negative. And inside here, this is a volume. We're going to indicate it by omega, and the surface, we're going to indicate it by partial omega. These are kind of mathematical symbols for the volume and for the surface. And then we'll now conserve the total mass. What we're going to assert is that the total mass is not destroyed, so the rate of change with respect to time is equal to 0 for the total mass. And the total mass has two parts, one that's inside and one that is crossing the surface, in or out. So if we write it down, the conservation equation here, we're going to write it as an integral over the volume of the rate of change of the total mass. Total mass is the integration of the density times an element of volume. So we integrate the density over the entire volume. That gives you the total mass that is inside this object that we're looking at right here. And this volume integration is the rate of change. So the rate of change is 0 if we don't have fluxes going in or out. If we have a flux of matter that is going out, then this rate of change is going to be negative. So if this rate of change is going to be changing, but it will be decreasing, negative. So it will be negative, the integral over the surface now of the flux of matter that goes out. And the flux of matter is the J mass, the mass flux, dotted with the surface area. So we're going to dot this vector here with the surface area, which is n ds. So we will have integration of J dot n ds, and that is the mass flux that is leaving the surface. So this is a statement of conservation of mass on a inside and outside. The total sum, if we just add up what's happening inside, what's happening outside, we should have 0. So that's the statement of conservation. Now we can see the value of Gauss's theorem because I have a surface flux for the matter that is going out, and I have a volume integral to determine the entire mass and its change with respect to time. So for me to actually talk in the same terms, I'm going to have to convert the surface integral to a volume integral, and that introduces the divergence of the mass flux. So I'll have the following. So if I collect this term and put it on the other side and convert it at the same time using Gauss's theorem, I have one volume integral of the mass rho d omega, and then I have another now plus another volume integral of the divergence of J mass Jm, and this is over the omega equals to 0. And that is the statement now of the mass conservation. So this is an integral form, and it should be valid for any particular location regardless, and therefore the summation has to be 0 identically for any position in space. And this is called the localization principle. Like you have an integral form, the integration of the sum of these two quantities must be equal to 0. The only guarantee that we have is that the two quantities themselves in any particular part of space should be equal to 0 identically, and that localizes the integral form to a differential form. So we can just use this idea, and then now remove the integral, and then we have now the rate of change of rho with respect to time, because we don't have an integral, plus the divergence of the Jm. It should be equal to 0. And then I have to express what Jm is. This is a drift flux, and the drift flux is proportional to the velocity. Now I don't have species, so it's just the total system has a velocity v. So I have now can write it d by dt, d rho by dt, plus the divergence. The J now has two terms. One term is the total mass, and the other term is the velocity, and that should be equal to 0. So when I take the divergence of the product of two functions, it's just like normal derivatives. It will be the first times the divergence of the second, plus the second times the divergence of the first. So I will have d rho by dt plus rho times the divergence of the velocity. So I'm going to put it here in parentheses, plus now the velocity times the divergence of the density. And this is now a dot product because I have to have a scalar here. This will be equal to 0. So this will be two vectors. This the divergence of the density is a scalar. So let me take that back. So this will be basically, let me take it back. Here I write it correctly. V times the divergence of the density. So I have here the gradient of the density, because I have to have now the gradient of the density would be a vector, and the vector dotted with the velocity that gives us a scalar, because originally this is a scalar, and the scalar, you apply the chain rule, but you apply it so that the result is also scalar. So in order for the result to be scalar, you have to have rho is a scalar times the divergence of the velocity, that's a scalar. And then the other one is v. V is a vector, so we must have a dot product with another vector, which is the gradient of the density. And that is equal to 0. So we have now this kind of expression. And we note here that there are two terms that are can be collected together, and these two terms are here: the rate of change of the density and the v times the gradient of the density. We can collect them together, and we can collect them together in a symbolic form by writing that d by dt plus, this is an operator now, plus v dot grad. So v dot grad, the gradient, and this is multiplied by rho. So this is basically adding the two together. We have d by dt plus v dot grad times rho. It means operating on rho, plus rho times the divergence of v. This is equal to 0. Now, if you look at this form that I obtained here, the first two terms, I'm going to highlight here these two, are combined together. It is the rate of change with respect to time, absolutely in the reference frame, plus the change material, the change in the density due to the motion itself, due to the motion by the velocity. When we add these two together, we have equivalent would be a derivative called the material time derivative or the substantive derivative. So we are going to use this idea here to rewrite the conservation law in this form. So we're going to, let me just kind of clear this page and then write it. Now I have, instead of having the two terms, I'm going to use capital D by capital DT of rho plus rho times the divergence of V is equal to 0. So this will be the conservation equation that we have. Note that d over dt is the same as partial by dt plus v dot grad, and that's kind of what represents, I'm gonna show you here, this represents the material derivative that we have in our system. So we have the material derivative here, and the material derivative, we're going to use it with the capital D. And we note that if we have a stationary frame of reference, then material derivative here, this is material, is the same as the reference frame derivative, time derivative. So in this case, we have basically a situation where we have the two terms together. Let me just put myself back here. And we have these two derivatives that we will take care of. and we will see that we want to now simplify it a little bit more. So to simplify this conservation equation some more, I'm going to have to look at what is the divergence of the velocity vector v. And I'm going to take an assumption in the following, that we have an incompressible fluid. So if we're talking about casting, for example, that's a pretty good assumption. If we talk about chemical vapor deposition, that's going to be a poor assumption. So for casting, then we would use an incompressible fluid approximation. And for incompressible fluids, we are going to look at the divergence of the velocity vector v and show that it is identically equal to 0 for an incompressible fluid. So let's try to do that. And in doing so, I'm going to start from the volume integral form, so the integral of the divergence of v over the volume. We want to check this out when we have incompressibility condition. So this is the divergence is now I can write it as the time rate of change of the divergence of the position vector r d omega. Note that dr by dt is equal to v, so I just pulled the d by dt out. The divergence of r is going to be very interesting to note. The divergence of r. Divergence is d by dx, as we mentioned, and d by dy, and d by dz in the beginning of this lecture, with 3 components. We have x, we have y, we have z, so we get a factor of 3. So we have like a constant number here, and the constant number is 3, which means that the integral of the divergence of v d omega is equal to d by dt times 3 times integral of d omega, and d omega is the total volume, so it'd be 3 d by dt of omega. And if omega is incompressible, then the volume does not change, and therefore we can see that this term is 0, and then we have a situation that the velocity, the divergence of the velocity vector, if for incompressible fluid, is equal to 0. And finally, now we can state the mass conservation equation in this form. Capital D by dt of rho is equal to 0, and this is obtained by assuming that we have an incompressible fluid. And in the case that the velocity is very small, like a creeping flow, or that we have a stationary fluid, then the capital D by dt will be equal to the standard partial derivative with respect to time of the total density. And that would complete our derivation for the conservation principle of the total density of the system. And we'll just continue in the next lecture to look at what happens to species conservations.